Have you ever noticed how once you learn to ride a bike, picking up something like a scooter or maybe even ice skating feels, well, easier?
Yeah, definitely.
Like your brain isn't just learning that one specific skill, it's somehow internalizing a more general way, like a strategy for learning similar things faster.
Right. Is learning how to learn those types of things.
Exactly. So the big question is, what if AI could do that? Could it learn how to learn new skills faster based on its experience?
And that right there is the fundamental idea behind what we're diving into today.
Hmm.
We're exploring the really fascinating field of meta-learning.
Often called learning to learn.
Precisely.
Okay, so our mission today is to unpack how this whole meta learning thing actually lets AI systems improve their own learning, how it gets around some of the big hurdles we see with traditional machine learning.
Especially when you don't have a ton of data to work with.
Right. We want to give you a clear, sort of concise handle on this field, what it is, the main ideas, and where it's actually making a difference out there. We've pulled together insights from quite a few expert sources for this deep dive.
Yeah, and it's important to understand the why first. Traditional machine learning models are amazing, no doubt. But they often struggle when you throw a completely new task at them, something they haven't seen before.
They need so much data, right? And tons of training time for every single specific thing you want them to do.
Exactly. They need massive data sets. And that training can be really long and computationally expensive. It's a huge bottleneck.
Yeah, I can see that, especially if like getting data is hard or expensive, or maybe the situation changes really fast. If you need a million photos just to teach an AI to spot a specific rare animal, like a pangolin.
Good example.
Yeah.
That's just not feasible for, say, a conservationist in the field.
Right.
And this is where meta-learning really changes the game. The core idea isn't just optimizing an AI for one task anymore. It's about empowering the system to actually improve its own learning process.
So it's not like a whole new category of learning, like supervised or unsupervised?
No, not really. Think of it more like a higher level framework, something you apply on top of those existing methods.
Okay, so it's giving AI that sort of human-like knack for learning to learn, like maybe a chef who knows basic techniques and can just whip up new dishes easily.
That's a great analogy. The AI learns transferable knowledge. It becomes a better learner for future tasks, especially if those tasks come from a similar sort of distribution or family of tasks.
Gotcha. So to really get this, maybe we should break down the key terms, like what's a base learner?
Right. The base learner is just the underlying AI model that's actually doing the specific job, like image recognition or maybe language translation.
Okay, the model doing the work. Then what's the meta learner?
The meta learner is the component sitting on top. It learns the meta knowledge, the strategy, basically to make that base learner better and faster at learning new things. It optimizes the learning process itself.
And it doesn't train on just one big data set for one job?
No, exactly. It trains on what's called a metadata set. And this isn't just a big pile of data. It's a collection of many different but related tasks. Each task is like a mini learning episode for the meta learner.
And the key idea is that these tasks, they all come from some common task distribution.
Yes, that assumption is crucial because the meta learner learns patterns across these tasks. It can then generalize that learning strategy to new tasks, ones it hasn't seen before, as long as they sort of fit that same general distribution.
So there's a meta-training phase where it learns this strategy.
Right, acquiring the meta-knowledge.
And then a meta-testing phase to see if it actually works on brand new tasks.
Exactly. You evaluate how quickly and well it can adapt using that learn-to-strategy.
So the meta-learner isn't just learning tasks, it's figuring out how to learn them efficiently. And the outcome of that is it develops this sort of general starting point, like a universal prior or inductive bias.
Yes, precisely. It acquires this generalized knowledge or a broadly applicable learning strategy that gives it a significant head start when tackling a new related task.
Yeah.
It's not just a small improvement, it's often a fundamental shift in capability.
Okay, this is where it gets really interesting, connecting to things like few-shot and zero-shot learning, right? Because if it has this head start.
Absolutely. Meta-learning is a key enabler for models that can learn effectively from just a tiny amount of data that's few-shot learning. Or sometimes even with no specific examples for a new task, which is zero-shot learning.
So few-shot learning, that means the model can figure things out from, what, just a handful of examples, like maybe 1 to 5 pictures per category?
Typically, yes. Imagine trying to teach an AI to recognize a new, extremely rare bird species. With few-shot learning, maybe just seeing one or two photos is enough for it to generalize. That really opens up possibilities where data is super scarce.
Wow. And zero-shot learning goes even further. How does that work with no examples?
Yeah, it's pretty mind-bending. The model makes predictions on new categories it's never been explicitly trained on. It has to rely on that universal prior or other contextual knowledge it learned during meta-training, maybe understanding semantic relationships between concepts.
Okay, that's the what and why. But how does the AI actually do this learning to learn? Our sources mention sort of three main approaches.
That's right. Generally, they fall into three buckets: metric-based, model-based, and optimization-based meta-learning.
Let's start with metric-based. What's the core idea there?
Metric-based is all about learning a good way to measure similarity, a robust distance metric. The goal is to map inputs into a space, an embedding space, where things that are alike are close together mathematically and things that are different are far apart.
So it learns to categorize new things by comparing them to examples it's already seen, using this learned sense of distance. Like, this new thing looks closer to the dog examples than the cat examples.
Exactly. It infers relationships based on proximity in this learned space.
Okay, that sounds really useful for things like finding similar images or maybe facial recognition, right?
Definitely. Common algorithms here are things like prototypical networks. They calculate an average representation, a prototype, for each class, and then classify new things based on how close they are to these prototypes. Or Siamese networks, which learn by trying to pull similar examples together and push dissimilar ones apart in the embedding space.
And the big advantage is data efficiency for few-shot tasks.
Yes, that's a major strength.
Okay, what about the second type, model-based meta-learning?
Model-based approaches focus on designing the actual neural network architecture to be inherently good at adapting quickly. They often incorporate things like an external memory module.
Like inspired by human working memory. So the model can quickly store and retrieve information it needs during a single learning task.
Precisely. Think of networks like memory-augmented neural networks, or MANNs, or certain types of recurrent neural networks like LSTMs that are specifically designed for meta-learning tasks, sometimes called RLWO, or LSTM meta-learners.
And the benefit there is mostly about rapid adaptation, especially maybe for sequential data, like in reinforcement learning where an agent has to adapt to a changing environment.
Exactly. That rapid adaptation is key, making them well-suited for reinforcement learning agents needing to adjust to new scenarios quickly.
Okay, that leaves the third category, optimization-based meta-learning. This sounds fundamental.
It really is. Here, the focus is on learning or adjusting the optimization algorithm itself, how the model updates its parameters to make learning from few examples much more effective and efficient.
So it's like a hierarchy. The base model learns its task parameters, but the meta-learner optimizes how the base model starts learning, like finding the best initial parameter settings, or maybe even tuning the learning rates.
Yes, exactly that. It optimizes things like the parameter initialization, or the learning rates, or even the update rules across many different tasks. It's enabling AI systems to become, in a sense, self-improving at a really deep level.
It's a pretty amazing concept, AI optimizing how it learns, not just what it learns. And within this optimization category, there are a couple of really famous algorithms, right? MML.
Yes, model-agnostic meta-learning, or MML, is hugely influential, introduced by Chelsea Finn and colleagues in 2017. A key feature is that it's model-agnostic.
What does model-agnostic mean in practice? Does that mean it's flexible?
It means it can be applied to basically any neural network that uses gradient descent for training, which is most of them. ML's main goal is to find an optimal initial point for the model's parameters.
So like a really good starting place.
Exactly. A set of initial weights that are highly sensitive and allow the model to fine-tune very quickly and effectively to a wide range of new tasks, were just a few examples.
Okay, powerful. But how does it find that optimal starting point? It uses this two-loop optimization process, right? Can you unpack that a bit?
Sure. So first you have the inner loop. This is where the task-specific adaptation happens. For each task you pull from your metadata set, you take the current metaparameters and you quickly adapt them using just a small amount of data from that specific task, the support set.
So a few quick learning steps just for that one task.
Right. Usually just a small number of gradient updates. This gives you temporary, task-specific, adapted parameters.
Okay, that's the fast adaptation part. But how does it learn the general starting point from that? Where does the meta part come in?
That's the outer loop, the meta-optimization step.
Yeah.
After you've done the inner loop adaptation for a task, you evaluate how well those adaptive parameters perform on different data from the same task, the query set. You calculate a loss, based on that performance, the meta loss. And this loss is used to update the original shared metaparameters, the starting point we talked about.
Ah, I see. So the outer loop is adjusting the initial parameters so that after the inner loop's quick adaptation, the model performs well across many different tasks.
Precisely. The goal is to find an initialization that consistently leads to good performance after just a little bit of fine-tuning on any new task from the distribution. MML's big innovation was training models to be easy to fine-tune.
Not just training them to perform well directly, but training them to be ready to learn quickly. That's clever.
It really is. And it's been applied successfully to few-shot image classification, like recognizing those pangolins regression problems, and even reinforcement learning, teaching robots new tricks quickly.
But you mentioned earlier this sounds computationally expensive. Updating all those parameters, second-order derivatives, that sounds like a hurdle.
It definitely is, or at least it was initially. MAML does have substantial computational cost. Calculating those gradients through the inner loop updates, which often require second-order derivatives, is intensive, both computationally and in terms of memory, especially for big networks. And it can sometimes be unstable to train.
Have people found ways around that?
Oh yes, there's been a lot of follow-up work, things like MAML plus WA, which tweaked how the outer loss is calculated to improve stability. And then there's ANIL, almost no inner loop.
Almost no inner loop. What does that do?
It drastically cuts the cost by only adapting a small part of the model in the inner loop, usually just the final layer or head of the network, while keeping the main body frozen. This is much, much faster.
Okay, so ANIL makes it more practical. But MAML isn't the only game in town for optimization-based meta-learning, right? There's Reptile.
That's right. Reptile came out of OpenAI. It's often described as a simpler yet remarkably effective alternative to MAML. It's known for being easier to implement and more computationally efficient.
Simpler is often good. How does Reptile work differently? It also aims for a good starting point, right?
Yes, the goal is similar. Find an initial set of parameters that allows for fast adaptation. But its approach is different. Reptile iteratively samples a task. Then it performs several steps, say k steps, where k is greater than 1 of standard gradient descent on that task.
Okay, standard SGD for a few steps. Then what?
Then it takes the original model parameters, the metaparameters, and nudges them slightly towards the parameters it ended up with after those k steps on the task. It's like taking a small step in the direction of the task-specific solution.
Ah, okay. So compared to MML, how does that change the optimization? MML calculates gradients through the inner loop, right?
Exactly. MML often needs those second-order gradients because the outer loop update depends on how the inner loop gradients change. Reptile simplifies this considerably. It just does standard SGD within the task and then does a simple update of the initial parameters towards the task-optimized ones. No second derivatives, no unrolling computation graphs in the same complex way.
So it sounds much lighter computationally, less memory, easier to code.
Generally, yes. It's often more computationally efficient, requires less memory, and is definitely simpler to implement.
Okay, but the big question, does simpler mean less effective? How does the performance compare to MAML?
This is the surprising part. In many cases, Reptile yields performance comparable to MAML. It can even converge faster sometimes. There might be scenarios maybe with very complex task distributions where MAML has a slight edge, but for many practical problems, Reptile's accuracy is nearly identical.
Wow. So why does that simple approach work so well? You mentioned needing K1 steps is important.
Yes, that's key.
Yeah.
If you only did one step, K1, it would basically just be like training on all tasks jointly, which isn't as effective for learning adaptation. Doing multiple steps implicitly encourages finding an initialization point that is close to the optimal solutions for many different tasks. Mathematically, it relates to maximizing the inner product of gradients from different mini-batches within a task.
Fascinating. And where is Reptile used? Similar areas to MAML.
Pretty much. Few-shot classification benchmarks like Omniglot and Mini-ImageNet, and also reinforcement learning. There's a cool example of using it to train an AI to quickly learn new levels in Super Mario Bros.
Okay, so whether it's MML, Reptile, or other methods, this whole learning to learn capability seems like it could unlock a lot.
Oh, absolutely. The impact is potentially huge across many different fields.
We touched on computer vision, recognizing rare species like pangolins, or maybe new parts on an assembly line from just a few examples. Also, facial recognition, semantic segmentation.
Right, and in natural language processing, NLP, it's boosting things like text classification, figuring out sentiment, for instance, improving machine translation, especially adapting to new languages or dialects quickly. Text summarization, too.
I read about AI assistants that can learn your writing style almost instantly.
Yeah, potentially. By analyzing just a few emails, it could adapt to mimic your tone or style. That's the kind of personalization meta-learning enables.
And in reinforcement learning, you mentioned agents adapting to new environments,
Exactly, making AI agents much better at adapting quickly and efficiently. Think robots learning new ways to handle objects.
like picking up a screwdriver after learning to pick up a cup.
Yes, without needing a whole new long training phase.
Hmm.
Or autonomous cars adapting to unexpected road conditions. Or game AI learning new strategies on the fly.
That's really powerful. What about areas like healthcare?
Huge potential there, allowing predictive models to adapt quickly to new medical conditions, new patterns in patient data, maybe emerging diseases. It could really accelerate diagnosis,
Hmm.
especially for rare diseases where you only have a handful of cases to learn from.
And personalized recommendations, like on streaming services or shopping sites?
Definitely. Faster adaptation to your specific tastes and behavior with less data means much more tailored and relevant recommendations, potentially much quicker.
It's even used in AutoML, right?
Yeah.
Helping to automate the process of building machine learning models itself.
Yes, it's leveraged to optimize things like choosing the right model architecture or tuning hyperparameters, making the whole ML development process faster. Google's AutoML project uses related ideas.
And it ties into lifelong learning, too, helping models keep learning new things without forgetting everything they knew before.
Exactly. It helps models continuously update while trying to avoid that catastrophic forgetting problem. It's really about creating more adaptable, resilient AI. And this ability to do more with less data, to adapt quickly, it kind of democratizes AI, doesn't it? Makes powerful capabilities more accessible.
It does seem that way, but it can't be all smooth sailing. What are the big challenges or limitations right now?
Well, computational complexity is still a major one, as we discussed, especially for the more complex methods like MAML on large models. It's getting better, but it's still a significant barrier.
Okay, what else?
Generalization is another big one. Sometimes models meta-overfit. They get really good at adapting to tasks similar to the ones in their meta-training set, but then struggle when faced with a task that's truly different from outside that initial distribution.
Ah, so it learns the meta strategy too well for the training tasks.
Kind of, yeah. It overfits the distribution of tasks it was trained on.
And there's that sort of paradox of data dependency too, right? It helps models learn from few examples per task, but the meta learning itself still needs a lot of different tasks to train on initially.
Exactly. You need a diverse, high-quality metadata set to train the meta-learner effectively in the first place. So the data requirement shifts from needing lots of data per task to needing lots of diverse tasks.
Makes sense. Any other big hurdles?
Yeah, a few more. Interpretability is tough.
Ah,
It's hard to understand exactly why a meta-learner arrives at a particular learning strategy. Also, dealing with real-world situations where the types of tasks might change over time, non-stationary task distributions, is still an active research area. And like all ML, potential for bias inherited from the meta-training data is a concern.
okay, so quite a few challenges still. Where is the research heading to tackle these? What's exciting on the horizon?
Well, a lot of work focuses on enhancing scalability and efficiency, obviously, developing lighter algorithms, better parallelization techniques, maybe online meta-learning, where the model adapts its learning strategy continuously.
And making them better at generalizing, handling those shifts in task types.
Yes, improving transferability and robustness to domain shifts is critical for real-world use. Developing algorithms specifically designed to handle situations where the task distribution changes, like ROML or MOCA.
Are people combining the different approaches like metric-based and optimization-based?
Absolutely. Hybrid approaches are a promising direction, trying to get the best of all worlds, and exploring new architectures, like using transformers for meta-learning, or further improvements to memory-augmented networks.
And thinking about how humans and AI might work together.
Yeah, enabling systems that adapt more dynamically to individual user preferences or needs is a big focus. Plus, of course, ongoing work on the ethical side, identifying and mitigating potential biases, and just pushing the boundaries of few-shot and zero-shot learning even further.
It really feels like meta-learning is becoming a core piece of the broader AI puzzle, weaving into large models, distributed systems, continuous learning.
It definitely seems to be moving that way. It's less of a niche technique and more of a fundamental capability we want AI systems to have.
Before we wrap up, maybe quickly clarify the difference between meta-learning and something like transfer learning. People might confuse them.
That's a good point. They're related but distinct. Transfer learning usually means you pre-train a model on a massive data set, like ImageNet, And then you take that pre-trained model and fine-tune it on your specific, smaller target tasks.
So you transfer the learned features or representations.
Exactly. It works well if your target task is reasonably similar to the pre-training task. But it might not adapt as quickly or effectively if the tasks are very different, or if you only have very few examples for the target task.
Whereas meta-learning.
Meta-learning is explicitly trained to be good at adapting. It learns an efficient learning algorithm or a highly adaptable initial state, rather than just learning static features. This generally makes it more robust when adapting to diverse tasks, especially in the very low data regime.
But they're not mutually exclusive.
Not at all.
Huh.
In fact, hybrid approaches that use pre-trained models as a starting point for meta-learning are becoming increasingly common, trying to get the benefits of both.
Okay, that helps clarify. So, wrapping things up, meta-learning really seems like a major shift, moving AI towards systems that don't just do things, but actually learn how to learn, tackling data scarcity and enabling much faster adaptation.
It's a profound evolution, enabling AI to be more flexible, efficient, and ultimately more intelligent in a broader sense.
It leaves you wondering, if AI can truly master learning how to learn, what does that imply for the future pace of discovery? Could the next big breakthroughs come not just from smarter AI, but from AI that gets smarter faster?
That's definitely a powerful thought to consider as this technology continues to develop.
We really hope this deep dive gave you a solid understanding of meta-learning, what it is, how it works, and why it matters. Definitely subscribe to the deep dive for more sessions like this, where we break down complex topics.
Yeah, hope it was useful.
And hey, if you're looking for more AI content, maybe some hands-on tutorials or deeper dives, check out the YouTube channel, Ian Ochieng AI. That's Ian. Then Ochieng spelled O-C-H-I-E-N-G AI. Thanks for joining us, and until next time, keep learning.